about this in special cases, you're not going to see me write this. It'll be understood that the input to S1 and S2 is x of t. That's what this diagram means. We also have a new system over here. We have a 2-input, 1-output system. And I think it's pretty obvious what it is. It's an adder. So if we were to call this Y1, the output of that system, and that Y2, then Y was Y1 plus Y2. So that's what an adder does. I think it's pretty self-explanatory in the terms of this, what's called block diagram. So a parallel system has 2 systems in parallel, each having the same input x, and you just add up their outputs to produce the total output. So for example, suppose you wanted to model an echo chamber. So in that case, the system S1 would, let's say, do nothing. Its output is equal to the input. The output of S2, or rather S2 would be a delay box. It would delay its input. After you add them together, you get the same signal plus itself delayed. That's what happens when you have an echo. You get a signal plus its delayed version. So I could construct something out of very simple systems that's a bit more complicated. Okay, finally, we have the most complicated structure that we're going to encounter, the feedback. And I'll explain how it's used in a second, but let's go through this. So we have the input, and there's the output. The input is going to go through an adder, and the other input to the adder comes from something derived from Y. So the way we think about this is that this output of this adder is an error signal, because you can see this little minus sign sitting here. Well, that's the standard convention, which means that the E is equal to X minus the output of S2. So that little minus sign right there corresponds to that minus sign. So that's how you indicate a difference instead of a sum. So what this feedback configuration does is it takes E, passes it through S1 to produce the output. But that output gets fed back through S2 to occur at the input. That gets subtracted from X and produces the error signal, which goes round and round and round and round. So this is the way a cruise control works on a car. You may change the setting for the velocity at which you want the car to go, and if that is different than its current velocity, that produces an error signal. That causes the engine to rev. Let's say that describes the engine, causing an output velocity y, but that goes through the control system S2 to produce the error signal. And finally, when the error goes to 0, the cruise control kind of settles down and doesn't accelerate the car anymore. So that's a great example of a feedback system. I want to point out that everything I just said in that example wasn't electrical. Turns out systems can describe a very general class of signal. The fundamental reason is they're just mathematical constructs. And system theory and signal theory, for that matter, applies to electrical signals and beyond. So it's interesting that you can use these kind of models to describe much more general things. All right, let's talk about special cases, special systems. And perhaps one of the most important are linear systems. Let's look at this. So we have a system S. If it is linear, if you take an input that consists of a sum of inputs, sum of signals, so x1 is a signal, x2 is a signal, and a2 and a1 are scalars, constants. The output to that sum is the sum of the outputs to the simple signals. So if you put in x1 by itself into S, you get that for an output. put in S2 by itself, you get that. You add those two together with the weighting constants, that's the same as if the system saw this sum presented to it as an input. So this is a very important property of linear systems. It's called the principle of superposition. We're going to use this a lot. We've already seen, when we talked about signals, that it's very convenient in many ways to think about signals as a sum of simpler signals. So for example, that triangular signal we saw in the signals video, we wrote as a sum of 3 signals. Well, to find out what the output to some system is to that signal, all I have to do is figure out the output to a step and to a ramp and a delayed ramp, add them all up, and that's going to be output to our complicated signal. So this principle of superposition is very, very important. It helps decompose problems. Once you can decompose a signal into simpler parts, you now can find the output because you probably can easily find the output to a simple signal. So here's the some special cases of the linear system. Let's assume that the linear system here, S, is linear. If you multiply the input by a number, you change its amplitude, well, the output is going to be the output you had before multiplied by the same gain factor. And there's a way, almost sloppy way of saying this: you double the input, you double the output. If that happens, then the system could be linear. If that does not happen, if doubling the input does not double the output, then the system can't be linear. It violates the rules. That's a special case of what I wrote up here, because here we have A2 is 0 for the case that I'm showing down here. Okay, then the other case is just as I described in some detail. If you just decompose a signal into a sum, its output of the system, the system's output to that sum is the sum of the outputs to each. So that goes just to the detail of what we said before. But this result, turns out, has a very interesting consequence. So let's consider a special case. A2 is the negative of A1. And let's say that x1 and x2 are the same thing. We're just going to call that x. So A1 and A2 are negatives of each other, and these two signals are the same thing. Well, what that gives us is that the input to our system is A1x minus A1x. Well, that's called 0. But now, let's look at what the linear system equation says in that special case. Since x1 and x2 are the same, we have s of x, and then they're weighted by the same A1, but they're subtracted to get 0. So if the system is linear, you stick in 0, identically 0, into a linear system. What you get out is 0. Any system which doesn't obey that rule cannot be linear. So if you stick in 0 and the output is 1, that system is not linear. It's sort of a very simple test, but it's not what's called sufficient. It's a necessary property, but not sufficient. The real test of whether something is linear or not goes back to the original definition. And by the way, in detail, this principle of superposition has to apply for all signals x1 and x2 and all constants a1 and a2. So it's a pretty demanding requirement, but when you have a linear system, it's very, very nice. Now, another special class of systems are so-called time invariant systems. So what these kind of systems are is that if you come into the lab, let's say, and you build a device and you put in an input and you measure what the output is, you leave the system alone, you come back the next day, You put in the same